So mostly we associate torque with rigid bodies rotating around a fixed axis with some kind of a rotational push to make the body spin. Now in this lesson we will define torque when it acts on a particle that moves along any trajectory relative to a fixed point and not necessarily a fixed axis. Also, this trajectory need not be a circle anymore, and it could be any path the particle takes around a point about which we are trying to find the torque. And since torque is a vector, it can point in any direction depending on the situation. So consider this particle at point A in an xy plane and a force F that acts on the particle in the same plane, which means force F is in the xy plane as well. Then if the particle's position can be defined by a position vector r, the torque that acts on the particle relative to the fixed point O will be a vector quantity that can be expressed as a cross product of r and F. So a couple of things to keep in mind. One, we are finding the torque acting on the particle about this point O, even though the origin and the point are not connected physically. Also, torque is a vector quantity, and therefore you must remember that it is always to be taken as r cross F, and this order should not be changed. That is, never do an F cross r to find the torque. Now, we are quite familiar with how we find the direction of torque. That is, we slide the vector F without changing its direction until the two vectors are tail to tail. And then we can make use of the right hand rule by sweeping the fingers of the right hand from R, that is the first vector in this formation, towards vector F, that is the second vector. And when you do this, the thumb gives the direction of the torque. And here we can see that it is in the positive direction of the z-axis. So for complete clarity, let us quickly see this short video that explains how you can find the direction of the cross product. The vector product or the cross product between two vectors A and B that are 5 degrees apart is written as A cross B, and the result of this operation is a third vector C that equals AB sine phi. So the resultant vector C is perpendicular to both the vectors A and B. Now you might think that vector perpendicular to A and B could be in this direction, or it could be in this direction as well. So to determine the correct direction, this is what you do. Put your right hand along vector A, which is the first vector appearing in A cross B, like this. That is, the base of the hand aligns with vector A and the palm of your hand faces vector B. Then you sweep your hand from vector A towards vector B like this. Then the direction of the thumb is the correct direction of the resultant vector C. And of course, the magnitude of torque would be R F sine phi. And you must remember that phi is the smaller of the two angles between the direction of R and F, because it could be this or this. So you need to take the smaller of the two. And some of my students have asked the significance of sine phi, or why do we take cross product at all? So the explanation is that by doing so, that is taking the cross product, sine phi helps us isolate the part of F that's perpendicular to R. Remember, torque depends on this perpendicular force to produce rotation. So if phi is 0, that is, it becomes a parallel vector, guess what? No torque, nothing turns. Now, there are two alternative ways to think about torque. And let us call the first one as the perpendicular force component way. So what we can see is that this side, let us call it F perpendicular, is nothing but F sine phi. And therefore, if you rewrite this expression like this, you can also calculate torque as the product of R and F perpendicular, or R and the component of F perpendicular to R. So think of F perpendicular as the effective push causing the rotation. The second way of interpreting or calculating torque is the moment arm way. So here we can see that this side, let us label it R perpendicular, is equal to R sine phi. And therefore, this time if you rearrange this equation like this, torque can also be written as R perpendicular times F. And often this quantity is referred to as the moment arm of F, or the perpendicular distance between O and the line of action of F, or the shortest distance from the fixed point O to the line of action of the force F. And a quick real-world example I can give is, imagine pushing open a door, and if you push near the hinge, that is small moment arm, it's hard to turn, it's more difficult to turn. But push further from the hinge, that is big moment arm, it rotates easily. That is, R perpendicular is in action. So you see, both these ways are nothing but use of simple high school trigonometry to write this equation in two more ways, and therefore have two different physical interpretations for the idea of torque. So if you really want to understand rotation, including rolling without slipping, angular momentum, etc., I would suggest you head over to this playlist that has all the lessons you need to master this topic. And if you like this video, do give a thumbs up, and I'll see you in the next video.